Let me say at the outset, thank you all for coming. Welcome to the first Math Club meeting. We will not have one next weekend because I learned years ago you don't mess with First Friday. So, how many of your freshmen you know what First Friday is? Yeah, it's like they have a parade. And you got to get out of here if you want to get out. Otherwise, you're kind of stuck in the parade, right? So, anyway, after that. Starting September 15th, I think, we have a really, I think, kind of exciting sequence of talks. I don't say series of talks because perhaps they don't add up. See what I did with that. But it ought to be a fun semester. So I'm going to start off talking about sets and counting. So let me ask y'all this. When I say the word set, what does that mean to you?
Put something on the table. Set it on the table.
What's that?
When you take something and put it on the table, you set it on the table.
How about the noun version? So naively, this is kind of a notion that we've got in math is a collection of objects. Such that if I walk up to you on the street and show you an object, you can tell me whether or not it's in the set, right? It's a well-defined collection of objects. Now that's a little bit naive. This actually develops some problems, but we're just going to go with that definition from the beginning. Okay, we'll just say that our naive notion of a set is just a collection of things, and I can determine if something in the universe is in that set or not in the set. So that's what we're going to go with at first. So a simple example, the set of all people in this room with blue eyes, right? And so I can tell if somebody's in the set or not in the set, right? The people in the room that are currently standing, I can tell who's in the set, who's not in the set. And this set is varying as time goes on. So let me ask you this. So I could consider set of all whole numbers. I could consider the set of all rational numbers. I could consider the set of all oak leaves on planet Earth, right? Things like that. Let me ask you kind of an interesting question. Has anybody ever thought of a set that has that contains itself as an object? So, for example, you might consider the set of all people in this room, right? Is the set of all people in this room an element in that set? No, because the set of all people in this room is not an individual person in the set, right? How about the set of all whole numbers? That doesn't contain itself as a set, does it? Because, well, the set of whole numbers is not an individual whole number. Can anybody think of, with our naive definition of set theory, an example of a set that might contain itself as an element? Yeah.
Set of all sets.
The set of all sets, if such a thing exists. How about this? The set of all abstract thoughts. That is itself an abstract thought, is it not? Right? But actually, it turns out that there's a bit of a problem with that. And we're going to talk about that later. So, set contains objects, which are often called elements of the set. We like to count. Okay. See if you guys can see. How many pieces of chalk do I have in my hand? 3, right? Counting fractional pieces of chalk. I've got 3 pieces of chalk. So we all know how to count. You can count the number of people in the room, you can count the number of chairs in the room, et cetera, et cetera. So let me all ask you a question. In this hand, I have the set consisting of this eraser. In this hand, I've got the set consisting of my 3 pieces of chalk. Which has more elements in it? Everybody agree this one does. And how do you know that?
Speaking of counting.
I know that 1 is smaller than 3, right? So we can count. We can count elements in the set. Very clever. Now, let me ask you another question. Got a cinder block wall here wrapping around. Which set has more elements? The number of cinder blocks in the wall or the number of people in this room? Which one is more? Everybody seems very self-assured that it's cinder blocks, right? And I would have to agree with you. How many cinder blocks are there? How many people are there? You people didn't even bother to count. Nobody wants to count this. Why is it that you're so sure of yourself?
We can define a projection, that injection between important injection people to certain.
Can somebody straighten that out for me? How is it that without counting, we know there's more blocks than there are people? Right? What's that?
We say tentatively, those are small things like field, large cells. So,
Right.
so
let me ask you this. How many of you, directly or indirectly, kind of thought of it this way? If I were to compare the sets of people in this room versus blocks in the wall, and sort of think about it this way, if I kind of pair them off, I'm going to run out of people and have blocks left over. How many of you that was part of your thought process? Well, this is actually the more sophisticated way to count sets. Is instead of just using our numbers like 1, 2, 3, 3 pieces of chalk is more than 1 eraser. It might be better to pair things off, and we can do that as well. So I got 3 pieces of chalk. I got 1 eraser. Eraser pairs off with 1 piece of chalk. I'm out of stuff here, and I'm going to put it over. Right? That's another way we can do it without ever investigating what the cardinal numbers are. And so it turns out that this is sometimes a convenient way, maybe not to count, but to compare who's got the bigger set, right? Because I think we were all in agreement that there's more cinder blocks in the wall than there are people in the room, right? So that's this pairing off in our brains that we did kind of quickly. That's one way to compare sizes of sets. And when you talk about infinite sets, well, that's kind of the only. So let me give you some sets of numbers that you may have encountered in your travels. In case you're not used to these symbols, we have the natural numbers. Oh, just for dramatic purposes. Okay, this is the natural numbers with one more thing added to it. Right? We have the integers, which is all the integers. Runs in both directions. Right? We have the rational numbers. That's the real number. This is the set of I'll say real numbers. These are the numbers on the number line, right? Like you see the columns. Got the complex numbers. How many of you have seen complex numbers at some point in travel? Real number. And how about this? Okay, this is every possible subset of the rooms that I right. Any subset. Now, would everybody agree with me if I made the rather bold statement? These sets are all infinite. Right? These are all sets that are infinite. How would you compare them though? Right? Like we would compare the bricks to the people in the room. Would everybody agree with? I'm going to use this notation. Looks like absolute value, but what I mean by this notation is this is the number of elements in the set. So this is infinity. I agree with that. Maybe that last video is a little bit confusing, but can somebody explain why it should work this way intuitively?
Those sets use a number of contained.
Notice that the natural numbers is contained in here. All right. So I mean, it looks like everything we got here, and then there's something else. All right. And everything we've got here, and then there's a bunch else. Right. And everything here is a rational number, and everything here is a real number, and then so forth. This last one, I'll give a miss for a moment, but everybody okay with that? That's the way it should work. Let me get. Say, set S less than or equal to say 2. Yeah. Well, we can't count them really because these both have infinitely elements in it. If there exists a one-to-one function. Yeah. Okay. And this kind of makes sense because if you have the natural numbers and natural numbers in 0, everybody agrees that that's a one-to-one function, right? But notice that 0 is lonely, right? Nobody covers 0, right? So that's a little sad. And this brings me to like the Hilbert Hotel. How many of you have ever heard of the Hilbert Hotel? My brother actually is a hotel money bags kind of guy, and when his hotels are full, that's it. Right. Well, David Hilbert built a hotel that has infinitely many rooms, one for every positive integer. And suppose that he's going to make a lot of money off of this, right? Because infinitely many pennies, he makes a lot of money. But suppose this hotel is full, right? So he's got everybody, rooms one forever and ever, they're all filled up. And along comes one more guest. And Hilbert feels very sorry for the guest and wants to accommodate this guest. Can he do it?
Yes.
Can somebody describe a procedure for doing it?
Shoot them left to the next.
He's going to have angry guests because he's going to have to make him move. But new person comes into the Hilbert Hotel, and what do? You make the person in room one move to room two. Person in room two moves to room three. Person in room three moves to room four, and so forth. Now you vacated room one. It's always a little more room, right? Which is kind of crazy, right? It also highlights the difficulties you get in counting the finite versus counting the infinite. You can't do it. Can somebody, so suppose it's not just one person. Suppose that there's this big bus and let's say 80 people get on. Well, you could certainly accommodate 80 people by making the person in room one, or make all the first 80 people move down the road, right? And doing the same thing. What if infinitely many people got off the bus? Yeah, that's right. That's, I was hoping that you would answer that, but probably infinitely many people get off the bus. What do you do? Right. What you can do now, even if you've got infinitely many people counting that need the room, you can move one to room two, two to room four, three to room six. And so you can take every person and say, read the number on your room and move to twice that number. Right.
Each one's only room.
Right. That's, yeah, we won't have to go very well. The bigger your room number, the farther you got to go. So now, once you make those people move, how many rooms are unoccupied?
Enough.
Certainly enough. In fact, every odd number of rooms is now empty. Right? And so now you can accommodate countably many people. Right?
This time, Hilbert needs to make sure that it leaves some open.
Well, yeah, you can always do that. And of course, you can make it more sparse by sending, just tell everybody to read their room number and go to the square of that number. Right? Okay. So here's another illustration of, and this is kind of the advertisement that I gave. And this ought to kind of anger the blood a little bit, I think. All right, so I'm going to play this game. Now you can assume that I have superhuman abilities and I can go as fast as I can. But I'm going to play the following game. I've got this giant bag that can hold as much as I want. And I've got infinitely many ping pong balls. One numbered one, one numbered two, one numbered three. For every positive integer, I have a ping pong ball. Now, here is the game I'm going to play. At 1 minute to midnight, I'm going to put in balls number 1 through 10 in the bag. But then I'm going to immediately pull ball number 1 out. At a half a minute to midnight, I put in balls number 11 through 20, and I pull ball number 2 out. At a third of a minute to midnight, 21 through 30, and I pull ball 3 out. At a fourth of a minute, 31 through 40, and I pull ball 4 out. Does everybody understand the process? So effectively, at every iteration, I'm putting in 9 balls, am I not? How many balls are in that bag at the stroke of midnight? . Anyone want to take a guess?
No.
Okay, so some people are saying none, but after all, am I not putting in 9 balls effectively every time?
You'll never make it. Pick a ball.
Well, again, we're assuming it's like the Zeno's paradox. What happens is, of course, I have to do this process faster and faster, which is physically impossible in this universe, but this is math, so. Here is an elegant proof. There are no balls left in the bag. And here's a proof. Assume that there is at least 1 ball in the bag. Pull it out and read me the number. It can't be 1 because I pulled that out at a minute to midnight. It can't be 2 because I pulled that out at half a minute to midnight. It can't be 1/10 because I pulled that out at a 10th of a minute to midnight. It can be 1 over in. I pulled them all out. Now, here's the thing that ought to get you. Let me play the same game with a slight variant. At 1 minute to midnight, I pull in balls in 1 through 10 and I remove ball number 10. At a half a minute to midnight, I pull in 11 through 20 and I pull out 20. Then I put in 21 through 30 and remove 30, 31 through 40 and remove 40. How many balls now? Infinitely many. Because every number, every ball that has a number on it that doesn't end in 0 is left in the bag. That ought to anger up blood a little bit, right? Because what that shows is it matters what number is painted on the ball and what the algorithm that I use to take it out. But see, that's exactly one of the problems of counting the infinite in the following sense. Notice that this is a 1-to-1 function, and I did what came natural. Is there a 1-to-1 function that covers this whole thing?
N minus 1.
Right, let me see if I can, they've got me covered here. So I can do another map in white, it goes like this. 1 goes to 0, 2 goes to 1, 3 goes to 2, everything goes to N minus 1. This is a 1-to-1 map that covers everything. And this is a little bit different than what you're used to for finite. And this is a different thing about counting. I think we can all agree that there's the same number of elements in both these sets, 3 of them, right? So what does it mean for these 3 sets to be the same? There is a 1-to-1 map from here, and notice the 1-to-1 map covers everything, right? So basically everything's paired on. Agree? So 3 things here, 3 things here, there's a bijection here. There's this a 1-to-1 and onto. And this 1-to-1 and onto function, this is the whole idea with bricks. Everybody pairs off. Right? Same size. Now, let me contrast what happens in finite sets. Suppose do 2 sets of 5 things. Suppose I have a 1-to-1 map from here to here. That means that every different star has to go to a different X, right? Everybody agree that's a 1-to-1 map? What is also true about it? It's also onto. Every X is covered. No, there's no lonely X, right? In fact, if you have a finite set, if you have two sets of the same size in our finite set, both 5 elements, both 15 elements, whatever you like, if there's a one-to-one map from one set to the other, it's also onto sets of the same size. This does not have to happen for infinite sets. So, for example, these two sets, by my definition, are the same size because I compare them all. Right? Everybody agree? But this map, any one-to-one maps do not have to also be grouped. Because, for example, we can do this. And now one is long. It's not covered. You can't do this with finite sets. This is part of the problem that it says. So, well, so any questions? Okay, so let me give you some things that might surprise you. Even though this appears to have one extra, appears to have 0 we discussed, that's just an illusion of notation. These are the same size because there is, I can explicitly declare a function. This function right here, from the natural numbers of 0, is both one-to-one and onto, right? Everything over here is covered by something, and two different things here have to go to different things. Right? So we've got that. What about this? We intuitively saw this because there's certainly a one-to-one map from the natural numbers into the integers, right? Just take 1 to 1, 2 to 2, 3, and so forth and so on. However, that particular map, although one-to-one, doesn't cover every integer. What? So, are these the same size, or is this strictly smaller? Yeah.
If every even integer go to a positive, I mean every even natural number go to a positive integer, every odd natural number go to a negative number.
That's a great idea. Yeah, that's exactly right. In fact, I'm going to draw a picture so we can have some excitement in the math club. But this is basically your idea, right? So here are the integers. I'm going to circle. So I want to cover this by what the natural numbers. 1. So 1's going to go to here. 2, 3, 4, 5, 6, 7, 8, 9, and 1-to-1 and on to. Every integer is eventually covered, right? And there's no two natural numbers that go to the same, different natural numbers, different set. And so I think of this as sort of like a pattern like this. But yeah, you can give a formula, it's basically what you said. Notice basically by even ones, when you cut them in half, you get the positive. Whatever the formula is this, I guess you would take the minus sign of it, add 1 and divide by 2, see what that, right? But there you can actually write it supposed to. So, in fact, so voltage. What about the fractions? There's a number of ways to do this. Can anybody, well, what do you think? I mean, are the rationals honestly bigger than the integers? They're both infinite sets, or are they the same? So can we pair off the integers and the fractions? Yes.
You could use the p prime number and the q prime number and then find them together. Integer or something like that.
I'm going to give you a theorem here. I'm not going to prove this. This is kind of. I think it's good for me to kind of show you. If the denominator there exists f from s to p such that f is 1 and onto. We already know that. That's kind of our definition. But here's another way to think. If and only if there exists f from s to t and g from t to s, both 1 and 1. Proving this is actually a bit delicate, as a matter of fact. But really, what this means is S is less than or equal to T, right? Because there's a 1-1 map here. And this means T is less than or equal to S. And it turns out that works out to equality. But there's actually something to prove here. So I'm actually kind of being a little, I'm kind of blowing this off a little bit because there's some sophistication. But this probably does appeal to your intuition, right? Even for an infinite set, if S is less than or equal to T, size-wise, if T is less than or equal to S, then they should be the same, right? Given these 1-to-1 maps in both directions, you can actually use this to construct a bijection, but it's a mess.
That theorem has a lot of names next to it, right?
What's it?
That theorem has a lot.
Yeah, it's get all the guys attached to that. There's like
Schroeder, Bernstein.
yeah, Cantor Schroeder Bernstein. That's what it is. So, that's easy, right? We're not surprised here that the size of the integers is less than or equal to because they're included in the sets like that. Can anybody think of a 1-to-1 map of the rationals in T? And graduate students that are in my factorizations technique class should probably know that this is going to come. Here it is, kind of a groovy theory. I'll show you. I think this is kind of a fun map. All I have to do is be 1-to-1, and I'm done. Right? So what I'm going to do is I'm going to take a rational input. So I'm going to look at G of Q equals A, B, and integers A. I'm going to see the P. Okay, so I can write any rational number as A over B, where A and B are integers and B is greater than 0, right? Really what that's saying is that if the rational number is negative, I'm putting it on the numerator to be the negative part of it. Everybody okay with that? So here's what I'm going to do. And we'll also assume that A and B, because I want this to be well defined. So in other words, when I see a fraction, what I'm going to do is if it's negative, I'm going to make sure the numerator is negative part of it, right? And if the numerator is not 0, I'm going to make sure that the greatest common divisor of A and B is 1. So in other words, I'm never going to see a 2/4. I'll reduce that down to 1/2. I'll never see like a 9/12. So I'll reduce it to 3/4 and so forth. Okay, so here's how this is going to work. Adam, you like to participate? Give me a prime number.
751.
Is that prime?
Okay.
I'll try. You didn't even give my favorite prime. Jared, give me another prime. 37. Okay. Give me another prime that's not a list. All right. Okay. All right. Frank, give me another prime. 73. 3. Oh, that was the best number of all. And now I'll make it a prime. I've always got to give my shout out to Jenny. This is a wild, you can't prepare this function in any sensible way. What you do is you read the fraction. For example, if the fraction is 3/7, then the output of the function is 751 to the third times 37 to the 7. Right? If the fraction is negative, -1/4, then you get 5 to the first power, 73 to the fourth power. In the case of 0, you get 8 to the 7 power 3. Right? Right. Can somebody explain why this is 1-to-1? Yes.
It has to do with the fundamental theorem of arithmetic.
It's the fundamental theorem of arithmetic. Every positive integer 2 or greater can be factored uniquely with prime factor. So these are all primes, and these things are different. So there's no 2 of these you repeat because of the fundamental theorem of arithmetic. And notice that this occupies a very, very sparse part of the integers, right? It's only integers that are either a prime powers of 751 and 37, or 5 and 73, or this lone prime right here. Right? But this is a 1-to-1 map from Q into Z. Right? It's far from onto, but it's 1-to-1. So we now have, and so we get it, we follow it. So far, but now we turn an interesting corner. For the real numbers, it's different. As it turns out, Q is strictly smaller. So what that should tell you is there's actually more than one size infinity. There's the infinity, the minuscule infinity of the rational numbers, which is the same as the natural numbers. Now there's a bigger one. Real numbers is actually infinite, continuum. And this is an interesting proof. So see this. Suppose that Q, well, if I can look at this, suppose N, I can replace Q by N because now we know they're the same size. Then there is a bijection F from the natural numbers into R. Well, in fact, I'm going to go even further with this. I want to actually do this. I'm going to actually claim the size of the natural numbers is actually less than the size of the numbers and the interval from 0 to 1. I mean, not just the real, just in the number line, in the interval from 0 to 1. If not, there is a bijection F from N into one. By the way, can anybody think of a one-to-one map in the naturals in the 0 to 1? Everybody agree with that? Take every n to 1 over n, and you've got one problem because one isn't in there. Just take that to like, pi over 27 or one, right? Okay, so really what that means is if there's a bijection, that means that you can list the real numbers, the intervals 0 to 1. So F takes 1 to and 2 goes to A21, A22, A23, etc. 3 goes 3-1, A32, A33, and 1 goes. And in general, nth number n goes to AN1. And this is what's going on there. Now, can somebody tell me what the problem is? Can somebody see why it's not possible to list all these decimals? So this should be an exhaustive list, all decimals between 0 and 1, right? Yes.
And then diagonal take all dots A11, A22,
So I'm going to build and I'm going to call it this. And how am I going to build it? Well, let's choose. Let's say 1 if ANN is not equal to 1. And 6 if ANN. Right? So what do I do here? So what do I mean by this? I look at A11, which is the first decimal place here. If A11 is 1, Well, then I make it 6. So it'll be different from that. If A11 isn't 1, then I make that first decimal 1. Everybody agree with me? And this process. For all of us, and I built this. So note B1, B2, B3 is in 0, 1. In fact, it's a string of 1s and 6s. Yeah. But it's not. And how do I know that? Well, let's suppose that this new thing is in the list somewhere. Can it be this? No, because it doesn't agree in the first decimal. So because of this, I built first decimal to be different than that. It can't be that. Can it be this? No, because I made the second decimal miss this one. Can it be this? No, because I made the third decimal and so forth. So there has to be at least one thing left over. There's no way to pair the natural numbers off with even the real numbers between 0 and 1. So, any questions?
Well, let me see the interdiagonalization. Are there other proofs that they are making?
Oh yeah, there are other proofs. I want to up the voltage on this one a little bit, but now what we have is we have 2 infinite sets of this infinity is bigger. So is this the biggest infinity? Well, I'm going to give you a theorem that shows there are infinitely many sizes of infinity. So here's a theorem. Let S be any set, and PS is the set of all subsets. Then the size of the set is strictly less than the size of our set. Always. This is actually not too surprising for small sets, right? For example, if S is just this set here, 1, 2, 3, right? The power set of S is all subsets. And the subset, one subset of the set is the empty set, and then you've got the single element sets. And then you've got the 2 element subsets. Then you've got the whole shebang. By the way, how many subsets are there? There are 8. Right? By the way, does anybody know a formula? Just for fun? Right. If you start with a set, finite number, n elements, there will always be 2 to the n subsets. Right. So, I mean, this gets out of hand really quick, doesn't it? Right. Because even if you've got a set of only like 7 elements, there's 5,040 subsets. So the power set is much bigger, but we're still talking about finite sets. The proof of this for finite sets is actually pretty easy. You can do it by induction and a number of other things. You can just straight count it out. However, this is also true of infinite sets. And so if you look at a function Pick one of my subsets. Anyone you like.
Three.
Just by itself. Okay. Give me another. 1, 2, 3. And I'll pick 1, 1, 3. Notice that there's a 1-to-1 map from the set S, is the power set, but it's woefully not onto it, right? I mean, there's 5 things that are missing. Everybody agree with that? Okay. And I did this for a demonstration because I'm actually going to prove that this is true. Proof. There exists phi from S in power set S. Anybody define, tell me what's a good way to do a 1-to-1 function? That's right. Remember, always in math, if it ain't easy, don't do it. Take an element S out of the set. What am I going to do? I'm going to take it to exactly that element. So this shows that S is less than or equal to power set S. But now what I want to do to finish this off is to show that it is impossible to have a bijection. Suppose there exists F from S to PS such that F is onto. But actually, onto is the only thing that matters because it can never be onto. You can never cover it. And I am going to show this, and this is I love this proof. I am going to, so we've already got our function here, right? This is supposed to be a bijection going from S and covering every subset. We're going to define the set T, B, the set of stuff in S such that S is not in F of S. So it's all the elements that are not in the image set that they have. And this is why I did this example right here. For this function here, I mean, this is an addition for this function here. Let's check the definition, see what happens. We're looking for the stuff in the domain that's not an element of the image. Okay, is 1 in this set here? No. So 1 is in T. Is 2 in here? Yes, 2 is not in T. Is 3 in here? It's not in T. Okay, so T in this case is 1. Notice it could be the empty set, but T is just some subset, right? It's everything that when you plug it in, you don't see it over in the set on the other side. That's basically it, right? Now, what is special about this set? Since F is onto, I mean, this, I'm gonna have to take a shower after this proof. It makes me laugh. Since F is onto, there exists X in S such that F of X equals T. Everybody agree with that? Because T is a subset and it's got to be covered. All right, everybody agree with that? Maybe it's empty even, but it's a subset. It has to be covered. So check this out. Either X is in T or it's not. Right? Because T is a subset of S, so either X is there or not. So if X is in T, that means that X, if X is in here, that means that X is not in F of X, which equals T. Not in. So if X is in T, then X is not in T. All right. If not in T, then, and of course T is F of X by definition, if x is not in t, which is f of x, that means that by definition, x is in t. So if x is in t, then it can't be in t, but if it's not in t, it has to be in t. So what that means is this set can't possibly be in the image, which means that the power set is bigger. So if you start with the reals and you look at the subset of the reals, it's bigger. But guess what? This is a set too. You can take the power set of the reals, and maybe this goes on forever. Right? So not only are there different sizes of infinities, but there are infinitely many sizes. And I've taken too much time, but if you wanted to stay around and talk just for a bit about there's no set of all sets, that happens as well. I'd be happy to indulge you or me. Any questions? Yes.
How many power series would you need to take for the natural numbers to be the size of the reals?
Oh, that's a good question. The reals is power set of natural numbers, right? Here's another question. So you inspire one more question. So what we have, we did that Cantor diagonalization and we had this, right? Infinity, but this was a big one, right? Is there a set S with is there a size of infinity that's actually smaller than the reals, but actually bigger than natural numbers? Don't spray the giblet. You can't prove it. It is independent of the axiom. It has been proven that using the axioms of set theory that working mathematicians use, you can't prove the existence or the non-existence of such a set. It's called the continuum hypothesis. In fact, often I've heard, even in community algebra, I've heard papers where they'll say, oh, such as we're going to prove this result assuming the continuum hypothesis, which is fine because it's independent of set theory. But don't try to do that because if you can't prove it with just the axiom of set theory, right? Which is, this like really bothered a lot of mathematicians that you can't prove everything and there's always going to be statements that are undecidable, right? It causes great consternation in mathematics. To me, I just think it makes math a little sexier, right? Because you never know what you're going to get, right? Okay, any questions?
What is the cardinality of the set of all infinite cardinalities?
Google logic.
Yeah.
Other questions? Okay, rule of Math Club is all the pizza has to be gone. So if it's not, be a dorm hero and take it home with you, okay? I hope everybody has a great Labor Day weekend, and we've got first Friday next Friday, but after that, we'll resume our festivities. Holler at me out there if you got any questions.
Now the answer. What the